I'm Yvonne Stapp for Science for the Public, and I welcome you to our Contemporary Science Issues and Innovations program. Today, advanced telescopes, including the James Webb Space Telescope, are revealing the very early universe, and there are some surprises. Our guest, Julian Muñoz, explains why astronomers are scratching their heads and possibly preparing to revise current theories of the developments such as galaxy formation. Dr. Muñoz is an assistant professor of astronomy at the University of Texas, Austin, and he is a theoretical cosmologist working at the intersection of astrophysics and particle physics to investigate galaxy formation and dark matter microphysics in the cosmic dawn when the first stars formed. Dr. Muñoz uses data from the powerful James Webb and the Hubble Space Telescopes, and he is known particularly for his work on the 21-centimeter cosmology and dark matter and his participation in what's called the hydrogen epoch of the reionization array known as the HERA program. Dr. Muñoz, welcome, and thank you very much for joining us today.
Thank you for having me.
Okay, and I will start by just asking you, what's all this excitement about with the James Webb and what it has discovered about the very early universe that they're unexplainably early. These galaxies are too early or something. Could you tell us?
Yeah, so James Webb is a fantastic machine.
Yeah.
It's giving us eyes in the infrared, which we really didn't have before. I think if you're a member
With
of
the
the
Hubble
public
also.
who's interested, that's right. But if you're a member of the public who is interested in astronomy, you probably compare James Webb to Hubble.
Yeah.
And James Webb is bigger, more powerful.
Yeah.
But it's also giving us access to more farther infrared light. It's giving us access to all this redder light.
Yes.
Which, when you think about redder light, essentially allows you to do two amazing things. One is you can look further earlier in the universe. That's because as the universe expands, all the light from all the galaxies is expanding as well, so it's becoming redder. So James Webb lets us look further into the early universe. So further from us, earlier in cosmic history, closer to the very Big Bang. The other thing is because it's redder, you can also look at the same galaxies you were looking at before, but now you can see their older stars.
Yeah.
So Hubble was able to see galaxies, but mostly just the blue light. Blue light is emitted from very young, big stars. With James Webb, we can see the more common, so like most of the stars will be smaller, will be fainter, will be redder. And when you think of our sun is yellow, right? Stars even smaller than the sun will be redder. So James Webb is giving us access to these two new arenas to understand the universe. And things look weird. And this is, I think, a canonical thing that happens in science. It's a normal thing that happens in science. Whenever we build a new machine that can test new things, we find strange things because we haven't looked there before.
Yeah, right.
So James Webb is finding a population of very early galaxies. Very, very early, very, very big. And that's strange.
Right, and they don't seem to, they're not supposed to show up this early, I take it, right? Okay.
That's right.
A couple of things.
Some of these galaxies, yeah, go ahead, please.
Oh, no, go ahead.
I was going to say, some of these galaxies are too bright.
Yeah.
Which is to say, they're forming too many stars. They're like just, violently taking gas, forming it into stars, emitting light. And that's something that we could accommodate within our astrophysical models. You could imagine, you don't need to violate any law of physics. You just need to have gas that falls into galaxies maybe more efficiently than you expected. And, maybe that's not crazy. When you think of the universe, and you think the early universe, when you're closer to the Big Bang, think 100 million years after the Big Bang, as opposed to 14 billion years where we live now. The universe was denser. The universe was shorter-lived. So all these processes that happen in galaxies, imagine stars being formed, supernovae exploding, all these things are happening violently. They're happening very, very quickly.
Right.
So, it's not crazy that gas would fall into galaxies more violently as well.
Another couple of things about this very early universe that we don't hear that much about in the general public, and that is these important epochs or phases of what's called recombination and reionization. That's important for all of this, I think. Could you please tell us what those things are?
Of course, and this is some of my favorite things to talk about, so I'm very happy to add that. So the key player here is hydrogen. So hydrogen is the most common element in the universe, proton, electron. By mass, is 75% of all the gas in the universe. So again, key player, the MVP of the universe. So we track what happens to hydrogen, because that actually is what determines the sort of overall history of how galaxies form, how the cosmic web forms, how everything works in the universe. So early on, at the very, very early universe, taking like a minute or an hour after the Big Bang, the hydrogen is ionized. It's too hot, protons and electrons are moving around. But about 400,000 years after the Big Bang, for the first time the universe is cold enough that protons and electrons combine together for neutral hydrogen. And this is what allows the cosmic microwave background, the CMB, to be emitted. So this is a recombination about 400,000 years after the Big Bang. Now, if there were no galaxies in the universe, no stars, that would be the end of the story. Hydrogen would stay neutral forever. There'll be no life. It'll be boring. But there are stars. There are galaxies. So somewhere between 100 million years and 1 billion years after the Big Bang, stars form, galaxies form, they emit a lot of light, and they again separate protons and electrons. So this is called reionization, because it ionizes, separates the ions for the second time. That's the re part. And this is a critical phase transition of our universe, because again, hydrogen is the most abundant element, and it's all changing. It's going from being neutral atoms to being split ions. And to be quite frank, we don't know exactly how it happened. We have some sort of fossil evidence. We can see this in the CMB. We can see this in other observables. But we don't know when it happened, how it happened. We don't know who did it. And our current theory is that galaxies were able to do it. But again, here James Webb is also throwing a wrench into our plans.
I see. Right. So it raised more questions than you were expecting, I guess, huh? These theories are inadequate for the moment, from what you're seeing. That would you tell us about the number and the brightness of these galaxies? What's the problem here? It's apparently too early for that, and you have really targeted that in your work. Would you tell us about it?
Yes, that's right. This is something that we published. It appeared a couple of weeks ago on the journal. So the idea here is you have all these galaxies. This is by now a very well settled issue with James Webb. Whatever they come from, we're not sure yet, but there is more galaxies than we expected. They're brighter than we expected. Well, if you count how many photons, how many particles of light are emitted, turns out there's more than you expect, which kind of makes sense given what we know about galaxies. And when you do the accounting of when reionization should happen, it tells you that it's earlier than you expected. So this is to say, if you were to trust James Webb blindly, just take the results you see in James Webb, you would actually see that reionization should happen somewhere like 500 to 750 million years after the Big Bang, whereas the CMB tells us that it's about 1 billion. So there's a big difference, hundreds of millions of years earlier, if you trust James Webb blindly. Now, there's an important caveat here, which is that, of course, it's early data, all the things haven't settled yet, but this is pointing to a tension. There's a tension between what James Webb finds about the early universe and reionization and what is sort of like settled from more mature cosmological observables like the CMB. So there's something we don't understand in either the observations or the models.
Okay, so following that, then, you have pursued this in a slightly different way. You've raised an important question about why this is happening so early and that it just doesn't fit theories. And you brought up the issue of the too many photons, I think it was. So could you explain what you do in there to why you're raising that question, how you attack it?
Yeah. So what I do, I'm a theorist. So I look at what the data that my observational colleagues collect and then interpret it. So in this case, what you want to know is you want to know, when did hydrogen reionize? That's the question. Who did it? How did it happen? So what I do is I look at the data they collect. So how many galaxies they observe, where are they, what are their properties? And then given that with James Webb, you only see a tiny fraction of the universe, you have to study what would the whole universe do. So then you study, given what these galaxies have seen, when would the universe reionize? You do a calculation of how many light particles are emitted versus how many hydrogen atoms are emitted. You compare the two, and that tells you when would they be the same. When would the photons be enough that they would ionize the hydrogen? So the math is not that hard. It's accounting.
Yeah.
It's a little bit like if you're running the books for your company, money comes in, money goes out, it has to even out. There's the same thing, but now as photons come in, and then photons go out into ionizing hydrogen. This is why we call this paper a possible budget crisis. Because you're in a situation where you have more photons than you have hydrogen, so that looks weird.
Right. Now, your data is, this difference, you're taking from a radio telescope array. Is that correct? Is the Hera or the hydrogen?
No. So far, this was all with James Webb.
Oh, it was. So you could actually calculate that just from the James Webb. Okay.
Right. But I mean, as you can see, James Webb gives you questions.
Yeah.
And it can, because it can only. So James Webb is an infrared telescope.
Right.
So infrared and optical telescopes like James Webb can only see the light from galaxies.
Okay.
So you don't get to see the actual reionization happen. You only get to see how many galaxies there are, how many photons they emit.
Right.
If you want to actually see reionization, you need to look into these radio telescopes.
So that's a necessity then. That's not just something extra. It's really an important thing. And this is where you see the difference, evidently. See, one of the reasons for a difference. Could you please tell us about your work with this array and explain the array?
Yes, absolutely. It'd be my pleasure.
Okay.
So in addition to thinking about the James Webb Space Telescope, one of the most exciting observables and instruments we're going to have over the next decade are 21 centimeter experiments, which are radio experiments. So these are very different to your usual telescope. So I can actually show you what one of them looks like. This is the Hydrogen Epochal Reionization Array, or HERA.
Yes.
And this is a picture of it. This is an array. It's in a very radio quiet environment in South Africa. So it's very far. And as you see, this looks nothing like your usual telescope. You wouldn't see a mirror here. You wouldn't see anyone pointing anything. This is an array where each of these antennas is collecting radio light. So this is radio light from the very hydrogen that is being ionized in the early universe. And because the light comes from so far away, it's actually being redshifted. It's actually being stretched so that its wavelength today is like tens of feet. So you need this big antenna so you're able to collect this big radio wavelength. So I don't know if this picture gives you a sense of scale, but there's an array with about 300 antennas. And each antenna is like tens of feet in diameter. So you can see it compared here with some of the scientists and engineers that are building the array. So each of these collects a massive amount of area in the sky. And when you put them all together, the hope is that you can map the whole process of reionization. You can map the hydrogen through the universe in 3D, like full tomographic detail. Now, we still don't have a detection, but we're getting closer and closer to getting a detection. And this would directly probe the hydrogen. So it's very complementary to things like James Webb. You can think of James Webb is looking at individual galaxies and studying their properties. We can infer what's happening. This is directly looking at the hydrogen and telling us what's happening. So this is from a simulation in one of my papers on how the scales you can probe with 21 centimeter versus James Webb. They're very, very complementary. So this is one of the simulations of the 21 centimeter signal. And to give you a reference, these squares 4 billion light years on the side.
Wow.
So big chunk of the universe. This is what we can probe with things like this Hera experiment. And you see, red and blue means hotter or colder. So this is tracking how the hydrogen is being heated by extragalactic sources, how it's being ionized, all these things. So if you take this little corner here and you zoom in, you get this box. As you can see, it has a lot of tiny, beautiful structure in it. Then you get this little yellow corner, you zoom in again, and you get this structure here where you can see like galaxies will be forming here, bubbling, exciting the gas around it. What you can see with James Webb is of order one of these tiny little red squares. This is one pointing of the James Webb Space Telescope. So, of course, you're probing very, very different scales. With 21 centimeter, you get this thing on the left, you get this beautiful, rich 3D map, but at very large scales. With James Webb, you're seeing individual galaxies, one at a time, and that's probing very, very little scales. So if you want to understand reionization, you really want to combine the very large with the very small to understand all the physical processes happening in the early universe.
Wow. So that's quite a lot of work there. But now understand how they are really complementary, the James Webb, the optical and the array, that you really need both to penetrate this very, very early period, right? So
that's right.
That should be very productive. And I want to make sure we cover the dark matter in here too, but where are you now with this conflict? So your things are just happening too early. What's your best explanation so far? Do you have one? Except scratching your head.
I would say we need to understand better what the telescope is seeing. So we need to pay closer attention to the observations and actually understand what are the galaxy properties. How many are there truly? But on the other hand, I think we might have to revisit our models. One of the key uncertainties in this accounting, like photons in, photons out, is that hydrogen every once in a while will recombine. So proton and electron ions will run into each other and form neutral hydrogen again. We only have a theoretical understanding of how that happens, and there's a big gap in our knowledge.
Right.
So this could be an explanation, but there's something we need to understand.
Right. Okay, you got that now. Now, is there room here for dark matter? Why is that? What's the deal there? That's so important.
Good. So dark matter gives us the scaffolding to form galaxies. So all these galaxies that James Webb sees, all the galaxies we see today, they all live on a dark matter structure. So they give you the gravity. Without dark matter, galaxies wouldn't exist like we see them.
Right.
So one of the exciting things James Webb is allowing us to do is that it's probing early, tiny, faint galaxies. These galaxies will eventually grow, right, through cosmic history and become galaxies like we see today. But because we're seeing them so early, they're very small, and therefore their dark matter scaffolding is also very small. The reason why that's interesting is because we don't know what dark matter does in those tiny early moments. So the key to what dark matter is made of may actually be in understanding how many galaxies James Webb sees and what their properties are.
I see.
So there's a new angle of attack that James Webb is giving us that is complementary to all the other things we have, like the cosmic microwave background or the cosmic web. It's actually able to study these tiny dark matter structures at very early times, where if dark matter was weird, say dark matter interacted with itself or was hot and moving fast, that is where it would first show up. It would first show up in these tiny structures being altered. So James Webb is giving us access to those structures.
Okay. Is this helping you to understand dark matter itself any better? And could you tell us how much of what's the percentage of matter in the universe that is dark matter compared to us?
That's right. So out of all the matter in the universe, about 80% is dark and 20% is regular. Now, of course, there's a caveat to this, but it's all of the matter together, both dark and regular, is only about 30% of the cosmic pie. The other 70 is dark energy, which we haven't talked about at all.
Right.
But that is what produces the expansion of the universe and makes it accelerated. But dark matter is 80% of the regular of the matter, and regular matter is 20%. So again, dark matter is necessary for its gravity, and how much there is, we know, but we don't know what it is.
We don't know, right. And did you just suggest that it might have operated a little differently at the very beginning of the universe compared to how it acts as we think of it now or later?
That's right, but rather than different, I would think you're looking at different scales.
Okay.
So imagine that you have this scaffolding, and when you're making a huge building, you need a big scaffolding. So that's a galaxy today. It's a very big galaxy, big scaffolding. So if you're missing like a little bar here and there, maybe nothing will happen. But if you're looking at a tiny building where the scaffolding is very small, you need every single bar. Meaning, if you alter dark matter in any way, if you get rid of one of the bars of the scaffolding, the building may fall.
Right.
And this is what's happening with dark matter. When you look at early times, the buildings, the galaxies, are very tiny. So dark matter has to behave exactly, hold, and gravity and nothing else. When you alter it even a little bit, it's like you're removing bars from the scaffolding.
Yeah.
And the whole building may collapse.
Right. Okay.
So understanding this early building, these early galaxies, is a powerful way to see what dark matter is made of.
Right. You have to have the dark matter. We avoided talking about the dark energy because for us it's almost like another thing. But this is terribly important at the beginning. But you say that these galaxies were much smaller at this time. So but there's still a question of why they would form what seems to be so prematurely. Is that correct?
Mm-hmm.
All right.
That is right. Yeah.
And your answers for that, you need the dark matter for scaffolding, but that doesn't say anything about why everything forms so early. Is that correct?
That is right.
All right. And then do you have any answers, or do you anticipate, or is it too early to just say, well, what was happening there? You indicated you've got to get more data, obviously.
So there's two explanations, and again, they're both astrophysical, because even the most aggressive model of dark matter, it doesn't solve this. Like just the fact that there are more galaxies. Think of it like a scaffolding. If you make a scaffolding, you can make a building, but you cannot make more than one building. You build one scaffolding. So dark matter cannot give you more galaxies. It can give you fewer galaxies. So it goes the other way, essentially. Mm-hmm. Now, what you could ask is, you could say, well, astrophysically, how do I get more or fewer galaxies? So you can make galaxies be more efficient at forming stars, meaning, all these processes like supernovae that have feedback and explode the gas and throw it out, maybe they don't happen. Or you could have something where galaxies just burst on and off. Think of like an on-off switch in your room. Galaxies turn on, form a little star, then turn off, and then they turn on again, they turn off. And we still don't have an answer to which one is more important. Maybe both are important in the early universe. But we do think that early universe galaxies were both smaller and also more violent. Meaning there's reasons to expect that like these supernovae would turn them off very quickly, but they would turn on again. Like basically they're not like a stable thing emitting light like we're used to in the Milky Way. There's something that goes up and down very, very fast. Like again, like if you turn your switch of your room on and off many times.
I see. So, well, there are lots of unexplained things there, but what an exciting time to be working on this. It must be, having both the array, having both types of inspection must be wonderful for people, in this time.
It is, and the more data that we have, the better our understanding will be. So in this sense, the James Webb has been an incredible investment.
Yes.
To be able to look at the universe where we couldn't before.
Right. Just changes everything. And now, what are the next steps in terms of understanding the early universe? And you're involved with both of those ways of doing things.
Yeah, so I would say on the radio telescope side, on the Hera side, right now the team is analyzing very recent data collected over the last few years. And this should have enough sensitivity to either get a detection or a very good limit on what this signal is during reionization. So that will already be able to shed some light on the extension, like what James Webb is seeing.
Right.
So that is already on the works, and there's a big collaboration with 100 people or more. So you can imagine there's a lot of work that goes into this data.
Yeah, yeah.
Now, that's on the radio side.
Right.
On the James Webb infrared side, I think what is exciting is that it's a bit like the opposite. It's not a single collaboration. It's a lot of different scientists proposing time. So last week, actually, there was a deadline to submit proposals. And I expect that there's going to be a lot of different groups working on reionization, first galaxies. What should we observe? How do we observe it?
Yeah.
So the data comes in basically every day.
Yeah.
I can tell you a program I'm very excited about is called Glimpse. It's led by Hakeem Etek and John Chisholm. And there is a James Webb program that has targeted the faintest, earliest galaxies by using gravitational lensing. So the very idea that the gravity of a big cluster, focuses the light behind it and allows you to zoom in, essentially, to see fainter things like a magnifying glass would.
Wonderful.
This program, I think, is going to give us new, interesting insights on a regime of the universe we couldn't see before James Webb.
Oh, wow.
So I think when you put it together, the very big and the very small, that is how you're going to get a whole picture of how the universe formed and evolved.
Right. And it sounds as though you really are going to get some answers, too, within our foreseeable future here.
I hope so.
Sounds like
yes,
that.
Next few years.
Yeah,
Yes.
that's fabulous. That's fabulous. Again, what an exciting time to be working on this. And we're about out of time here. But Dr. Muñoz, I thank you so much. This was very clear, wonderful information for us. And I wish you all the best. And I predict big prizes for you in the future. I'm watching it. Okay.
It was my pleasure talking to you. Thank you for having me.